minutes, I propose we get started. It's a pleasure to have Alice here with us. Most of you have chatted with her, but I will briefly introduce her. So Alice was in our group and graduated from Yale back in 2013. She performed one of the first, if not the first, jet measurement in heavy ions at RHIC, and then went on to a fellowship at CERN and Heidelberg as postdoc, and is currently a senior lecturer in Lund University. And today she's working on Alice and is going to talk to us more about the work that she's doing there. Thank you.
I have lost my PowerPoint. Okay. Great, then it seems like it's time to get started. So thanks everybody for coming. It's really a pleasure to be back here at Yale at this wonderful place, see how everything has changed in the last 9 years. And to bring this talk to you today. So today I'm going to be talking about how we use heavy ion collisions and heavy ion physics to explore the phase diagram of nuclear matter. So let's start at the very beginning, just to make sure everybody's on the same page here. So what we're going to be talking about today is the temperature regime of quantum chromodynamics, QCD. Why is this so interesting? Well, it's because at normal temperatures, normal pressures, everything that we experience in our day-to-day life, quarks and gluons are confined into hadrons. So we never see these particles independently. We always see them contained inside the protons and neutrons of everyday life. But at high temperatures and densities, if we make a medium that is so hot, so dense, then these quarks and gluons are no longer confined, but instead can behave quasi-freely. And this creates a new extreme state of matter known as the quark-gluon plasma. So for example, let's take a look at this phase diagram over here on the right. This is just baryochemical potential versus temperature on the vertical axis. This little point here where it says nuclear matter, that's home, that's us, that's everything we experience in our normal life. But there is so much more out there if we are able to, for example, increase the temperature and explore the extreme reaches of the phase diagram of QCD. So in particular, today, we're going to be talking a little bit about this phase transition, about the critical point, and about this crossover, because we are going to be exploring up here on the high temperature axis and low baryochemical potential axis. So we believe that this phase transition between normal nuclear matter and a state in which quarks and gluons are the fundamental degrees of freedom happens around this critical temperature of TC. It's about 150 to 160 MeV. And you can really see from these theoretical calculations that, that we expect this phase transition to happen if we increase the temperature of our nuclear matter. So where can we experience these high temperatures and high pressures that would be necessary in order to find this deconfined state of matter? Well, we believe that this state existed maybe in the first couple microseconds after the Big Bang. We also have reasons to believe that it might exist under the pressures that are present in the cores of neutron stars. Or we can simulate the high temperature regime of QCD in simulations on supercomputers. Okay, but you know, the beginning of the universe, that's a long time ago. The neutron stars, those are awfully far away. Our supercomputers are giving us zeros and ones. Where can we make this stuff on Earth? Well, it's in collisions of heavy atomic nuclei at high energies. We also believe we can create this new state of matter. So first we need to create it, then we need to look at it. Where do we do that? Well, we have a couple of heavy ion colliders around the world. The main two are the Relativistic Heavy Ion Collider. This is located on Long Island, just outside of New York City. It's about a 4-kilometer collider in circumference. It mainly collides gold on gold nuclei at a wide range of center of mass energies, from 200 GeV, the top energy, all the way down to 7.7 GeV. But this is a beautiful and flexible machine and can collide a lot of other different types of particles as well. It can go all the way from proton-proton collisions up to uranium-uranium collisions. Now, the next generation of machine, of course, is the Large Hadron Collider located outside of Geneva. This is, about an order of magnitude bigger. It's almost 30 kilometers in circumference. There we collide lead on lead nuclei, and we have two different energies, 2.76 in center of mass energy and 5 TeV in center of mass energy. We don't have as much flexibility there, but we do also look at proton-proton collisions, proton-lead collisions, and even xenon-xenon collisions. So now we've made our heavy ion collisions, we have produced them. Now we need our camera. Now we need to detect what comes out of those collisions in order to study the fundamental physics that is ongoing there. So here are some examples of heavy ion detectors. So these are the ones at RHIC. The Phoenix detector has now been decommissioned, and the new S-Phoenix, or Super Phoenix detector, has been installed. But on the other hand, we have STAR, which is still running and still has an active physics program, at least for the next several years. And this is the main active detector at RHIC at the moment. If you need a sense of scale here, so this is a ladder, for example, and here is one also next to Phoenix. Now let's head over to the LHC and talk about the detectors over there. So the main dedicated heavy ion detector at the LHC is the Alice detector, which you can see here. But we also have the CMS and Atlas detectors, which are general purpose experiments, not built for heavy ion physics, but they do have active and very impressive heavy ion programs ongoing. You'll be seeing some results from them in a couple of slides as well. And even just recently, our friends over at LHCb have joined the game. So now all 4 LHC experiments are taking data in heavy ion collisions and producing results. So what kind of data do we get out of these types of detectors? Well, this is just an event display from a single lead-lead collision inside of the Alice detector. This is inside of our time projection chamber. That's the heart of our detector, which does all of the tracking for us. And you can see that in a single heavy ion collision, we produce thousands or tens of thousands of particles. And we want to identify and track all of them. So we will observe in our detector the spatial and momentum distributions of the final state particles, for example, pions, kaons, protons. And from that, we want to reconstruct all of the physics that went on in the initial collision. We want to figure out what was the initial state of our colliding nucleons. We want to figure out how the system evolved dynamically. We want to learn about its properties, both chemical and thermodynamic. And we want to learn about, for example, the interactions that charged probes have with our new state of matter. We also want to know fundamental questions like, how do those quarks and gluons recombine into hadrons? So in order to answer these questions, in order to reconstruct what happened in the collision itself, we need to take all of our tracks here and use those to reconstruct all possible final state particles, and then look at their correlations and at the numbers of particles that we find. So today I want to take you on a tour of a heavy ion collision. We're going to start out with the initial colliding nuclei. They're, Lorentz contracted into pancakes over here. In the first Fermi over C or so, they deposit their initial energy density into the initial state. That first Fermi over C is far outside of equilibrium. This is still kind of a mystery. We're not sure exactly how this exactly happens, but we're working on it. At some point, we have this initial energy deposition. It becomes a rapidly thermalizing medium that produces our QGP phase, which exists for a short amount of time. This QGP phase is expanding and cooling off very fast. And at some point, it becomes cool enough and diffuse enough that those quarks and gluons in our soup then recombine into hadrons. This hadronization happens, and then we have a further phase, which is the interactions in the hadron gas phase. But at some point, our system, which is still expanding and cooling off, eventually stops interacting, the particles get too far apart, and they fly and free stream to our detector. So I'm going to show you some important results from each of these phases and try and elaborate on the story of the evolution of heavy ion collisions today. So let's start at the very beginning. It's a very good place to start. Let's start with the initial energy density and how that evolves. In order to do this, I need to define just a couple of quantities that have to do with the geometry of my heavy ion collision. So the first thing to know is that not all heavy ion collisions are created equal. We have large we have large nuclei colliding, and these collisions can either be head-on, they can be what are called central collisions that have a big overlap region and produce lots of particles, or they can be more glancing collisions, and these are called peripheral collisions, where you have a smaller overlap region and fewer particles produced. Now, in those peripheral collisions, you can imagine that this overlap region, well, it's sort of shaped like an almond. It's not rotationally symmetric. It's not isotropic. It's actually an anisotropic interaction region. And you can define a plane of symmetry for this interaction region. This is known as the reaction plane or the event plane here. That goes along the minor axis of our ellipse or along the minor axis of our almond. This anisotropy in position space, well, you can imagine that anisotropic pressure gradients build up within our almond-shaped interaction region. And those pressure gradients are going to boost the particles outwards, preferentially along the plane of symmetry. And there are going to be less boost given to the particles that go perpendicular to the plane of symmetry. So you have stronger in-plane pressure gradients and more boost in-plane. What does this mean? This means that you would expect more particles to be produced along the plane of symmetry, which is actually what we see here in one of the very earliest results from the STAR experiment of RHIC. So if you look at the angle with respect to the plane of symmetry, you see more particles produced here. Then if you're looking perpendicular to the plane, that's sort of going upwards in our picture, you see fewer particles produced. Then you get back in plane and you see more particles produced. Actually, it's pretty cool because we see this phenomenon in other strongly interacting systems as well. This is just a picture of some ultra-cold lithium, which was kept in an almond-shaped trap. Then they release the trap, and you see how the ultra-cold atomic gases expand along the plane of symmetry. And this is the same thing that we're seeing here in our heavy ion collisions. It turns out that if we fit this curve with, let's say, a Fourier cosine series, the fits work out really well. And because we started out with this sort of almond shape, the main component in our fit is the one that goes with cosine of 2 times the angle with respect to the plane of symmetry. The coefficient for this term in our cosine series is called V2, and this is what we call elliptic flow. So elliptic flow has been measured in great detail as a function of, for example, the momentum of the particles, or the type of the particles, the species, or the centrality of our collision, among other things. And you see some early results here from the Alice experiment, where you see V2 measured as a function of the momentum for pions in red, kaons in green, and protons in blue. It turns out, this was a very big surprise, was that the measurements of V2 are described very well if you model our quark-gluon plasma as a liquid, if you apply hydrodynamic equations to our QGP. So this was the first shock. The second shock was that in order to fit the data well, as you can see here on this plot, you need eta over S, that's the shear viscosity to entropy density ratio, to be very, very small. In fact, near the quantum lower bound. So we not only say that our QGP behaves as a liquid, but it is the perfect liquid. It turns out that fluctuations in the initial positions of our nucleons actually mean that the story is more complicated than just V2. Sometimes you have events that look kind of triangular, or they look kind of like a clover or something like that. This leads to higher order coefficients such as V3 or V4 in your Fourier cosine series. And it turns out that these higher order coefficients are much more sensitive to the hydrodynamic properties and the dynamics of the QGP. For example, you could propose a temperature dependence of eta over S, and then use that to fit our V2, V3, and V4 data from STAR. And you see that depending on which temperature dependence you use, you get better or worse fits to the data. Now, this was kind of an early example of how we can use V2, V3, and V4 to constrain the hydrodynamic properties. Here's a more modern example. In fact, what they've done is they took the particle yields, the NDY, the mean PT, shown here, and the V2, V3, and V4, measured from Alice, as well as mean PT fluctuations. And they did a Bayesian analysis where they compared a model and varied all of the parameters in that model to fit the data. And they extracted, sorry, the pointer's not working very well. They extracted these parameters of the model that are required to fit the data with the best. Now, I don't know about you, I don't get much out of postage stamps, so I'm just going to show you the main result here. If I want to constrain the eta over S as a function of temperature, you see something that looks like this. And furthermore, they could also start to put some kind of constraints on zeta over S. This is the bulk viscosity to entropy density ratio. So we are now using our measurements to obtain the fundamental thermodynamic properties of our quark-gluon plasma medium. In fact, a cute little example is you can put the shear viscosity measured for the QGP on the same plot as other common materials such as helium and water, and you see that we are orders of magnitude lower. So again, this reiterates why the QGP is known as the perfect liquid. Maybe I give up. So we've talked about how the initial phase worked and how the initial dynamics of our system evolved. And we've learned a little bit about the viscosity of our system. Now let's say we want to actually probe the QGP itself. What do we do as physicists when we have a new medium and we want to know its properties? Well, we send in a probe. That can be an electron beam, maybe, poke it with a stick. I mean, whatever it takes, right? Send in a probe, see what happens. Now, our QGP is too small and it lives for too short a time to poke it with a stick. So we're not going to do that. Instead, we're going to use internally generated probes for our medium. These are the results of hard scatterings, high momentum transfer scatterings that happen in the early stages of the collision. So if you have quarks and gluons that collide with a high transverse momentum, then you will get back-to-back recoiling partons that separate like this. And those quarks or those gluons will then fragment into collimated clusters of hadrons. So essentially, you'll get two sprays of hadrons going in opposite directions. Now, that's what we know very well from proton-proton physics or E plus E minus physics, the creation, the production, and the fragmentation of jets. What if that jet happened in the early stages of a heavy ion collision? What if that jet was immersed in our QGP medium? Well, then the collision is going to happen here, and it's going to travel outwards through our medium. It's probably going to have some interactions. It might radiate off some additional particles here. And we can compare what jets look like in fundamental collisions with what they look like in heavy ion collisions. The modifications that our jets undergo in heavy ions is known as jet quenching or jet modification. And it really gives us insight into the properties of the QGP and how a colored probe, a quark or a gluon, interacts with the colored QGP medium. So we can see this actually just very basically from looking even at event displays. So here I take the calorimeter towers in CMS. I unroll my detector, and I take my cylindrical detector, and I basically just unroll it. And I see here a big spike in energy, which corresponds to a jet with about 200 GeV of energy. If I look back to back, 180 degrees away, then I find this jet over here, which has only 70 GeV of energy. Somehow these must have matched at the beginning. Conservation of energy and momentum tell us that. But the additional energy has been radiated away due to interactions with the medium. And this is the phenomenon known as jet quenching. So let's make this more quantitative here. Now, I can measure the following ratio. I'm going to measure the number of jets created in a heavy ion collision, just as a function of jet PT, for example. And I'm going to take the ratio with respect to the number of jets that I'm going to measure in a proton-proton collision, again, as a function of the PT. Now, I'm going to scale it by this number, which is called NCOL. That's the equivalent number of proton-proton collisions that I would need to stack together to get my heavy ion event. So you can imagine if jets were not modified by interactions with the QGP, this ratio should come out to 1. Should be unity in fact. But of course, we've now measured this in our experimental data, and take a look, for example, at this purple curve down here. These are the most central collisions measured by Atlas, and over a wide range in jet energies, you see significant suppression with respect to unity. So you see that the number of jets has really been suppressed or quenched by the interactions with the QGP medium. Now again, I want to make this a little bit more quantitative and ask what this can then tell us about the properties of the QGP medium. In order to do that, I'm actually going to make things a little bit simpler and go to hadrons. So high momentum hadrons are usually coming from jets, so we can kind of use high PT hadrons as a proxy for our jet measurement. So here I make the same kind of ratio where I calculate the number of hadrons measured as a function of PT in lead-lead or heavy ion collisions, and with respect to the number of hadrons that I would expect to come out of a proton-proton collision, again scaled by this number of collisions factor. And here's what I find. My charged hadrons are suppressed by about a factor of 2 at high PT. You might wonder, well, what about this scaling factor? Maybe I've got that wrong somewhere. But actually, what you see here is that the electroweak probes, the photons, the W and the Z bosons, are sitting right at unity because they don't interact strongly with the medium. So it really is the hadrons that come from my quarks and gluons, my hard scattered quarks and gluons, that undergo strong interactions with the medium that are being modified here. If I now take data, not only from the LHC, but also from RHIC, and compare it to a wide variety of models, as was done by the JET collaboration here, then you can use this ratio, this RAA factor, to extract what is called the jet transport coefficient, known as Q hat. So they've extracted these numbers. They're slightly different at RHIC and at the LHC. And you can see that for a quark jet with about 10 GeV of energy, you're going to lose about 1 GeV per Fermi at RHIC, or at these slightly lower temperatures, and about 2 GeV at the LHC energies. So now we have another pin in our properties of the QGP medium. We figured out how a colored probe loses energy and by how much when it interacts with our colored medium. So we've now extracted not only the viscosity, but also the jet transport coefficient here. So now I want to discuss just very briefly some other hard probes. So I had been looking at high momentum jets, which mostly come from the fragmentation of light quarks and gluons. But what about the heavy quarks? These might have very low PT, but they're still very large Q squared because of their large mass. So these are still hard probes. Let's now measure the ratio of our D mesons in heavy ion collisions as a function of the centrality. Central events are over here on the right and peripheral are over here on the left. And let's compare that with our non-prompt J psi. These are CC bar pairs that come from the decay of bottom quarks. And we actually see that both sets of heavy quarks are significantly suppressed. Again, the ratio is way below 1, but also that the suppression has a mass dependence. So the suppression for D mesons, which are coming from charm quarks, is much less than the suppression for the non-prompt J psi, which come from the decay of B hadrons. This is the well-known effect called the dead cone effect, and it was finally seen definitively here at the LHC. The interesting thing is, and I won't go too much into detail on this now, but we can talk about it later, is that the hard probes also seem to flow. So for example, you can measure the V2 of muons that come from Charm and muons that come from bottom quarks here. And there is a mass dependence for the V2 of these particles as well. So we really see that all of the hard probes, the heavy quarks and the jets, interact strongly with the medium and undergo modification or suppression. Okay. I want to show just one more example of the heavy quarks before moving on, because I think that this is a particularly beautiful result. Now I'm going to look at the suppression of upsilons. So these are BB bar charmonia. And if I just look at the invariant mass of my upsilon candidates decaying to 2 muons, then in proton-proton collisions, I will see 3 distinct peaks. These correspond to the different states, the upsilon 1s, 2s, and 3s. But if I do the same measurement in lead-lead collisions, well, I see that the 1s state is there, but is significantly suppressed. The 2s state, barely visible. The 3s state, gone. Our upsilons have completely melted inside of our hot and dense QGP medium. And that melting, that suppression is stronger for the states which are more weakly bound. The same can be seen if I actually measure just the REA for the 1s, the 2s, and the 3s state. You can't even see the 3s, you can only put upper limits on it. So now I've talked a bit about the properties of the QGP. I want to move on a little bit more in our timeline of heavy ion collisions. What happens when our QGP has expanded and cooled off such that the quarks and gluons have to recombine into hadrons? Well, if I want to measure now the chemical properties, so the types of hadrons that are produced by my QGP, I need to measure the identified particle spectra. So I show just one example here. This is the spectra for identified pions. Here in black, you see the proton-proton results. And in the rainbow colors, you see the most central events shown in red down to the most peripheral events shown in blue. Now, it's not just enough to measure pions. That's only just one particular set of particles. I actually want to measure all possible particles. So not just pions and kaons and protons. I also want to measure the nuclei, such as the deuterons. I want to measure the resonances, like the K0 stars. And I want to measure things like the 5, the SS bar charmonia. Then I want to measure the heavier states of baryons, such as the multi-strange psi and omega baryons. And there are more, but I just couldn't fit them on this slide anymore. Now, this is how I'm going to learn about the chemistry of my medium. In order to learn about the time at which the particle abundances were fixed, that is the time at which we had this change from quarks and gluons into hadrons. This is known as chemical freeze-out. And in order to learn about this, I need to measure the total hadron yield for as many species as possible. That means I have to extrapolate all of these curves down to PT equals 0, which is challenging but not impossible. And then I want to look at the total numbers of hadrons of each different type. And I'm going to compare that to a model. So here you can see in the total yield of pions, kaons, K0 shorts, the K stars, the 5 protons, then the rest of the baryons, so the strange lambda and the multi-strange psi and omega. And then here onto the nuclei, the deuterons, the hyperons, helium-3, and even helium-4. And I'm going to compare these particle yields, the numbers of particles of each different species, to a model which assumes purely democratic statistical particle production from a medium which is in complete thermal equilibrium and has a common freeze-out temperature, a common volume, and a common barychemical potential. So that is just nothing more than the statistical hadronization model. And if I compare this to all of my data points, you see excellent agreement with the data over more than 7 orders of magnitude here. So we can see now that the bulk of the particle production from our heavy ion events is coming from this sort of statistical, as I said, democratic particle production mechanism. And this puts another point on our map of heavy ion collisions, on our timeline of heavy ion collisions. We know the temperature at which this happens. Now let's say I move one step further. We talked about the chemical freeze out into the hadron gas phase. Now let's talk about at what time or what temperature the particles stop interacting, our hadrons stop interacting. This is known as the kinetic freeze out stage. So let's figure out when this happens, when the particles start to free stream to our detectors. For this, I'm not so interested in the chemistry of my system. I'm interested in the kinematic properties of my system. So as this is kinetic freeze out, I want to measure these kinematics with as much detail as possible. And what I'm going to do is I'm going to look at the kinetic spectrum or the PT spectrum in order to do this. This will tell me the final hadron kinematic. I can fit my particle spectra with what is called a blast wave model, a Boltzmann-Gibbs blast wave model. This is just a simplified hydrodynamic model. And I can fit several different particle species. Here, for example, I show pions, kaons, protons, and phis. And by using this simplified model, I can extract two parameters, the temperature, and I can extract the radial expansion velocity. So how fast my hadron gas is expanding. And you see a really nice trend here that as we go with increasing multiplicity up to central lead-lead collisions over here, you get lower kinetic freeze-out temperatures, but higher radial expansion velocities. And we can do this for several different systems. We've shown this not only in lead-lead collisions, shown here, but also in xenon-xenon, so smaller heavy nucleus collisions, and also in proton-proton collisions as well, which we'll come back to in a little while. So I hope I have given you a brief tour of some of the basic fundamental ideas and measurements and discoveries in our progression through the timeline of a heavy ion collision. I bet many of you noticed that I skipped a step, and that's the step I want to talk about right now. That is the phase transition from this quark-gluon plasma phase to the hadron gas phase. I'm not here talking about the recombination of quarks and gluons into hadrons. I'm talking about when and how does it happen that the fundamental degrees of freedom of my system stop being partons and start being hadrons. This brings us back to that phase diagram of nuclear matter. I want to find the phase transition line. So let's go back, as I said, to this phase diagram. I want to look for that phase transition. Theory can tell us quite a bit about this already. We know that at a small baryochemical potential, which is where our LHC collisions exist, we believe that this is a crossover transition between the deconfined and the confined phase, between the QGP and the hadron gas phase. Meanwhile, at higher baryochemical potentials, we believe that this is a first order phase transition. That means somewhere in between, we must have a critical point, the end of the first order phase transition line. And it is a big effort within our field to try and explore this full phase diagram, to find this phase transition, to find the critical point. It turns out that we got quite lucky at higher energies in that the theoretical prediction for where this phase boundary exists coincides with the hadronic freeze-out temperature. It's very, very close. And so that means that we hope that the signs of the critical behavior of this phase transition could be encoded into the yields of our final state hadrons. And that's what I'm going to discuss in the next couple of slides. The way we're going to look for this phase transition is through fluctuations. In particular, I'm going to be looking at the fluctuations of particle multiplicities as we look at different events. So event to event or event by event fluctuations. In general, these are used to study the properties and the phase structure of our strongly interacting matter. And why is that? Well, that's because it's actually quite a general concept in statistical mechanics, for example, that fluctuations grow in the region near a phase transition or near a critical point. So if we can find this growth in the fluctuations, then we can use that to pin down the location of our phase transition. You see this in many different materials. So not just in heavy ion collisions. This is the phenomenon known as critical opalescence, and I show it just here in carbon dioxide. For example, if you're higher than the critical temperature, the transition temperature in carbon dioxide, the gas is clear, right? But then as we lower the temperature down below the critical temperature, at some point the gas turns white. Why is that? Well, it's because you get a huge growth in the fluctuations of the density. And at some point, those fluctuations become so large that they're actually on the scale of the wavelength of visible light. That means that the light traveling through your gas gets scattered and your gas turns opaque. So this is the idea of critical opalescence, and we're looking for sort of a similar idea in the QGP. Finally, the other really important thing is that these fluctuations of conserved charges can be related to what are called susceptibilities. This is a thermodynamic property of any medium. And this is actually a thermodynamic property that can be calculated a priori using the fundamental theory of our field, QCD. So this allows us, it's one of the very few experimental observables that we can make a direct comparison between our experimental measurement and QCD as evaluated on a computational lattice. So let's try and measure these. Before I make any measurements, I need to talk about exactly what we're trying to measure. We're trying to measure these thermodynamic susceptibilities. As I said, these are properties of any thermodynamic medium. They, in general, describe the response of a thermalized system to changes in external fundamental properties. And here's the definition that I'm going to be using right now. The one we're most interested in is these susceptibilities called chi. They are the partial derivatives of the pressure with respect to the baryochemical potential. And this value, chi, for any order of the partial derivative, known as n, can be calculated within QCD. If I apply my ground canonical ensemble framework to the particles produced in a heavy ion collision, then I can relate the event-by-event fluctuations of the conserved charges to the susceptibilities within that are calculable. You might say, wait. You just talked about fluctuations of a conserved charge. How does that make sense? Well, don't worry. This is the grand canonical ensemble framework that I'm going to set up. So here is my rapidity distribution of all particles produced in an event. And I'm going to take a slice of my medium, of the particles that I observe. And I'm going to, for example, count how many baryons are in that slice and how many antibaryons are in that slice. Then I'm going to subtract number of baryons minus number of antibaryons. Now, if I look at the event as a whole, then baryons and antibaryons should be equal, right? So they are conserved, of course. But if I only look within this small slice, then the baryon number could be exchanged with the medium outside of my slice, which is my particle back. So particle number and energy can be exchanged with this particle back. And that's how I define my grand canonical ensemble. So when I say fluctuations of conserved charges, don't worry, it's only the fluctuations within a small slice that I define of my medium. So this is what I'm going to measure. In every event, I'm going to try and measure, for example, the number of baryons minus the number of antibaryons and calculate what is the distribution of this measurement. I could use baryon number, calculate number of baryons minus antibaryons, to understand what are the susceptibilities with respect to baryon number. And as a proxy, I could just count the number of protons. You know, I'm not so good at measuring neutrons, so I can just use protons as a proxy for my baryons. Let's say I wanted to measure the strangeness susceptibilities. Well, this is a conserved charge, of course. And so I could count up the number of strange mesons and baryons and calculate the fluctuations in those quantities. As a proxy, I could use kaons, for example. And I could also consider the fluctuations of electric charge, another conserved quantum number. For that, I would want to count charged particles, but in practice, I can use as a proxy my number of pions. And here I finally want to show how we connect the theory and the experiment. So here on the experimental side, I have the moments of my, in this case, net baryon distribution. The mean, the first moment, is proportional to the first order susceptibility, that first partial derivative here. If I take the second moment of my net baryon fluctuations, that is proportional to the chi2, the second partial derivative. Similarly, the third moment, which is the skewness, proportional to chi3. And the kurtosis, the fourth moment, is proportional to chi4. So if I can measure these higher moments of my net baryon multiplicity distribution, I can directly relate them to chi1, chi2, chi3, and chi4. But of course, it's not quite that easy because there are challenges here. Theory assumes that we have a fixed volume and an infinite particle bath within the ground canonical ensemble. Experimentally, we know that we have individual heavy ion collisions with a varying or fluctuating volume from collision to collision. And we know that, yeah, I mean, there are global conservation laws, of course. So if I look at all of the particles, baryon number has to be conserved. So there are some differences between theory and experiment, and it has been our job in the last several years to try and understand and account for these differences. What do we need? The main thing we need is really high precision. Because if we look at the second moment, you see very little difference between, for example, a hadron resonance gas and critical behavior from lattice QCD. There's no deviation between an expectation at the level of the second moments. If we look at the fourth order moments, you only see a 30% sort of deviation if we calculate, for example, the ratio of chi4 to chi2. So if we want to test lattice QCD with precision, we have to measure the fourth moments with better than 30% accuracy. But if we want to look for critical behavior, we need to go even higher, to the higher moments. So here I show, for example, again, this is chi4 over chi2, so the fourth moment divided by the second moment. And this is what is shown in black. And you see a fluctuation. You see these fluctuations grow in the region around the critical temperature. The sixth order moments, chi6 over chi2, grows even more in this green band around the critical temperature. Then let's look at the eighth order moments. Here's the same black curve as we saw before on the left, but the eighth order moments, you see a massive change around the location of the phase transition. So I want to go at least to the fourth moments in order to measure this. But again, remember, I have to do this with very high precision. So we need huge statistics, and we need to have very careful experimental control over all of our conditions. So we have to, again, start with the basics. We can't just leap directly to the eighth moments, no matter how much we want to. Instead, we're going to start with the second moments just to make sure everything is really under control. So this is the first measurement at Alice of the net proton second moments, shown here in red. Now, if everything about my proton production was purely statistical, if protons and antiprotons were produced completely independently according to Poisson statistics, then the difference, the net proton number, would be distributed with what is called a Skellum distribution. That's just the difference of two Poissonian distributions. And so my Skellum distribution, my Skellum expectation is shown here in the empty squares. If I take a ratio of my measured second moment distribution to the Skellum expectation, I get about a 5% deviation, which is shown, actually it's shown here in the bottom. So what does that tell us? We see that we don't have independent protons and antiproton production. Does this mean that we have correlations between protons and antiprotons? That's possible. Or maybe it's because our protons and antiprotons are not distributed with respect to a Poissonian distribution. Or maybe it's because we found critical behavior already. We found the phase transition. Great. Unfortunately, it's again not that simple, because we have to take into account the effect of these volume fluctuations, and we have to take into account global conservation laws like baryon number conservation. So in this paper, there was described a simple model that took into account volume fluctuations and global conservation laws, just using the number of protons, mean number of protons, and the mean number of antiprotons, and the centrality determination procedure. This model is shown here in the gray band. And you can see that it gives a perfectly consistent picture of this 5% deviation without need for criticality, without need for critical fluctuations or even correlations. So no phase transition yet, but of course we didn't expect it at the level of the second moments, so that's okay. Now what about the third moments? Again, we don't expect critical behavior at this point, but the third moments require even greater experimental control over our measurement, and therefore we have to go step by step to make sure that we are not doing anything that is outside of our control. For example, just the correction for tracking efficiency, so the efficiency of finding particles in the ALICE detector, leads to this difference between the measured values shown in the dark red and the open points, which is without the efficiency correction. So you can see just how well we have to know our tracking efficiency in order to get the third moments. Now the Skellum expectation for third moments is 0, and you can see that we've measured 0 with high accuracy. Not sure how much that helps us in our knowledge of 0, but it tells us that our understanding of our detector effects is precise within the level of less than 5%. So that's a really positive step forward as we look forward to going to the fourth moments. These are obviously very sensitive, but they give us confidence as we move to the fourth moments, which are the ones that are in progress right now. Of course, we can also do this at RHIC, not just at the LHC. And RHIC has published a whole suite of measurements of the net proton measurement. Of course, this is related to baryon number fluctuations. Net charge is related to the electric charge fluctuations, and net kaon related to the strangeness fluctuations or strangeness susceptibilities. Again, I don't get so much from postage stamps, so let's just focus on the main points here. I'm going to measure the third moments for my net proton distribution as a function of the collision energy. Why is that interesting? Because that scans the phase diagram of nuclear matter. So if I do this scan of the phase diagram, I hope that I get close to the phase transition or the critical point. So I measure my third moments here, and I do the same for the kurtosis, for the fourth moments. Okay, so we have a beautiful measurement of net proton fourth moments from STAR as a function of the collision energy. What's going on there? I see a big deviation from unity. Is this the sign of the critical behavior that we've been looking for all this time? Probably not, because I'm not jumping up and down. So again, hold your horses. Let's compare with that model that incorporates volume fluctuations and critical and conservation laws. That is what is shown in blue compared to the STAR data shown in red. And you see that these blue points exactly line up with the deviation from unity. We're still not sure what happens here at the lowest energies, the lowest collision energies. These points have moved around a little bit since this initial preliminary data, and the error bars are still large. So all the way down to a collision energy of 11.5 GeV, we see no deviation, no critical behavior. Still, the jury is out at these lower energies, and that's the reason why STAR is measuring these points with much higher precision. So let's take a brief outlook. Let's look where we're going from here. Runs 3 and 4 at the LHC will really allow us to expand these measurements and this search for the phase transition and the critical behavior to the fourth and the sixth moment of the net proton distribution with truly unprecedented precision. And this is the data that we're taking right now and the analyses that we're working on currently. Furthermore, at STAR, when they do the beam energy scan phase 2, which again is in progress right now, they will be able to shrink their error bars on the higher moments of the net proton distribution and allow us to look for these fluctuations over a wide range of the phase diagram. So the future is very bright for this type of analysis, and we hope that we will be able to pin down the location and the structure of the phase diagram of nuclear matter with this type of measurements in the future. So let me just give you an intermediate brief conclusion. I have tried to show you the main sort of points along the evolution of a heavy ion collision and tried to show how we can use fundamental experimental measurements to extract properties and information about the medium produced in these collisions. So I talked about how we use anisotropic flow coefficients to measure the shear and the bulk viscosity with help from our theory friends, of course. I showed how the hard probes, so jets and heavy flavor hadrons, are strongly suppressed due to interactions with the QGP phase. I was able to talk about the chemical and kinetic freeze-out points and how the model of statistical particle production at freeze-out describes our data over many orders of magnitude. And finally, I described in a bit more detail one of my favorite topics, which is how we use fluctuations to explore the phase diagram of nuclear matter. Now, I hope you'll allow me 5 more minutes to cover one more topic, which is also something very exciting, because it was also completely unexpected. Now, let's use what we've learned from heavy ion collisions, and let's go down all the way to the smallest systems and try and learn something very interesting there, and then take our knowledge back with us again. We were very happy with that story of heavy ion collisions that I just spent the last 45 minutes telling you about, until the LHC turned on. And suddenly, we did measurements of correlations in proton-proton collisions and in proton-lead collisions, and we saw something that looked like B2. Now, this is the type of plot that I haven't shown you before. This is the 2 particle correlations as a function of the relative azimuthal angle and the relative rapidity between them. What I'm looking at is that little shoulder structure there called the ridge. And these long-range correlations are very reminiscent of the flow signals that we observed in heavy ion collisions. So we're seeing something that looks like collective flow, or at least collective behavior in high multiplicity proton-proton and proton-lead collisions as well. This was a big shock for all of us who thought that proton-proton collisions were boring and that they were just our baseline, right? Okay, so we see collective behavior here. We saw one other interesting feature in these small collision systems. We saw what is known as strangeness enhancement. So the number of strange particles was always expected in heavy ion collisions to be enhanced with respect to proton-proton collisions. This was viewed as a signature of QGP formation within some models such as the MIT bag model, and this was worked out by Rafelsky back in the 1980s. This was the historical motivation for measuring strangeness enhancement. Now we actually understand it's not about the enhancement in large systems, it's actually that the strangeness is canonically suppressed in small systems, but the effect is basically the same. We thought this was a signature of QGP formation in heavy ion collision. But in fact, when we measured these ratios of strange hadrons, sorry, the picture quality is not so great, strange hadrons like the lambda, the psi, and the omega, and looked at the ratio with respect to the pion yield as a function of multiplicity, we saw a smooth turn on all the way from proton-proton collisions to proton-lead collisions to lead-lead collisions. So we saw this big increase in the strangeness production, even within the small systems, proton-proton collisions. And this smooth turn on of strangeness enhancement made all of us scratch our heads. What does this mean? Does this mean that there's maybe a non-hydrodynamic, non-QGP-like explanation for our heavy ion collisions? Are our heavy ion collisions nothing more than just a bunch of proton-proton collisions put together? Is there an alternative description for heavy ion collisions, a more detailed one than the nice story that I presented to you in the beginning of my talk? Or is there maybe QGP-like physics happening in small systems? Does that mean our understanding, our basic model of proton-proton collisions was somehow incomplete? This really shows the complementarity between doing heavy ion collisions and analyses and the analyses in small systems like proton-proton, because one will teach us about the other. And the question I want to leave you with, because I don't have all the answers, none of us have all of the answers on these big open questions, is how then can we use our knowledge of heavy ion collisions to improve our understanding of proton-proton physics and vice versa? So this has really opened up a big doorway into a new area in our field to explore this question in more detail. So finally, I've now added one more observation to my conclusion slide, and that is that we see these QGP-like signals in the small systems as well. We see these flow-like coefficients, and we see the strangeness enhancement in small systems. And I want to know how we can use that observation to then learn more about these same signals in heavy ions. We will be able to do this with advancements in both of our experimental measurements and within with our theoretical modeling. So I will give just one more outlook to, again, run 3 and beyond at the LHC. We're expecting a 10 times increase in luminosity in the next runs at the LHC, and we will be able to make really precision measurements of jets to tell us about energy loss and modification. For example, using photon tag jets, as I show here in a projection from Atlas. We will be able to use heavy flavor hadrons and look at those hard probes to study the interactions with the medium and the hadronization property of our heavy flavor. So the same precision that we could find with the strangeness sector in runs 1 and 2, we're now going to obtain in the charm and maybe even the bottom sector with runs of 3 and 4. Next, we will also be continuing to look at correlations and fluctuations. It's not for runs 3 and 4, but even beyond in run 5, we will be able to extend our fluctuations measurements into the charm sector and look for the fluctuations of thermalized charm. This will give us more access to properties of the QGP, like the charm susceptibilities. And finally, we'll also be able to use electromagnetic probes, such as in this projection from Alice here, in order to study much more about the electromagnetic radiation from our QGP. So if you want more information, we have a lot more of these projections here in our yellow report. Finally, as I said, a big open question is what is going on in small systems? One of the questions is we see these collective, Vn coefficients, but we don't yet see energy loss in these small systems. We want to increase our experimental precision in order to look for this jet energy loss. We will do that in the future at the LHC using more data in proton-proton, proton-lead, and even in oxygen-oxygen collisions. And in order to take advantage of these, the higher luminosity heavy ion data, the higher luminosity proton-proton data, we will need to do major detector upgrades. So the Alice detector recently reinstalled the heart of the detector. We rebuilt the heart of our tracking system, and that is now running for data collection in the current runs 3 and 4. And Atlas and CMS have big upgrades planned for the next long shutdown as well. And finally, with all of these advances in the measurements as well as in the theory, our goal here is to really try and get a unified description of the QGP from the macroscopic level all the way down to the fundamentals of quantum chromodynamics at the microscopic level. And that is the goal of our field, going from all the way from heavy ion collisions down to proton-proton collisions and back again. So I have added one more thing to my conclusion slide, and that is that the future is bright. We have upgrades for future physics discoveries in place and more on the way. And we are finally entering the precision era of really studying extreme QCD in detail with all of the experiments at the LHC as well as at Lund. So thank you very much.
We have time for a few questions.
Thanks for the nice talk. So I have a question regarding the RAA of D0 and gate size. So is the difference due to mass ordering, or would there also be contribution from like recombination effect?
Here the difference here that we observe is due to the mass difference between the C and the B, because here the J psi are coming from B hadrons. So they're coming from the decay of hadrons, which consist of a B quark and an up or a down quark. Meanwhile, the D zeros are a combination of a C quark and an up or a down quark. So there's no difference in recombination effects between these guys.
So what's the composition of J psi?
CC bar.
But it's decay from B hadron.
Yeah, these are exactly. So there are higher order states that contain B quarks, and then those B quarks decay, and then okay, yeah, maybe you see a little bit of the recombination effect there because they need to pick up a tron quark somewhere. Okay.
One more question.
You can go.
Okay, can you go with the study team? I'm kind of hoping you can clear up a long confusion of mine as like a CF expert. But so you have these VNs here, and then you have the like the, I guess, multi-particle cumulant. So I've heard these described two ways, and I can't figure out if these two ways mean the same thing or if these are different methods with the same notation. But I've heard this as the like second digit can either be like the statistical cumulant of the VN, or it can be like that order correlation. So if you have like V2, 4, be like a fourth cumulant or like a 4-particle correlation.
Right.
Can you shed a little light on this?
Right, exactly. So these are the multi-harmonic, but the multi-particle correlations, and you can calculate V2 from 4-particle correlations where you subtract the 2-particle correlations of those.
Okay.
Yes. So it is the cumulant instance that you're asking about.
So those are like the same thing then?
Yeah.
Or okay. Interesting.
I have a question on slide 27. You can tell that Katie and I are both writing our theses. So if you're looking at the transport coefficient for like Q hat at like the Q hat over the temperature, like Q is higher at RHIC. And then when you look at it just for a quark jet, it's somehow like the ordering flips. I guess because quark jets would be in greater abundance at RHIC than the LHC, so I'm kind of surprised that the quark number is not like somehow closer to the overall number at RHIC than at the LHC. Maybe that question doesn't make sense. Just because those top numbers would be a composition of both like quark and gluon initiated jets, right? And if RHIC is dominated by a quark jet sample, then why is that number not close?
I think that the difference between the top value for Q hat over temperature cubed and the bottom, which is Q hat, is not in the quark versus gluonness of it. Okay. I think it's because you have the different temperatures.
Okay, so you're saying that number basically like will dominate, like the difference, like the smaller temperature.
Exactly. Okay.
Is there anybody in the outside that may have a question? Maybe like 30 seconds.
If they say anything, it's going to deafen us. I don't know.
If not, maybe we should just thank Alice for a wonderful. All
right, thank you, everybody.
Thanks, everybody. On the